So it's our pleasure to invite Peter to give a talk today. So he'll be talking about no occurrence obstructions for determinant versus permanent. The floor is yours, Peter.
Okay, thank you, Kevi. Thank you very much for the invitation to this event. So I will report about this joint result with Christian Nickemeyer and Greta Panova that we obtained a couple of years ago, actually 5 years ago, if I'm not mistaken. And then I think there was also a journal version which appeared 3 years ago. So when I looked, you know, I took some effort to look at the paper. Some of the details are quite intricate, but I try my best to give an overview. Sometimes it's better to forget the details for explaining the ideas.
Yeah.
So here is the outline. So I understand I have 75 minutes.
Yeah.
So feel free, if there are questions, feel free to interrupt me. I didn't bring too many slides. So the idea is maybe one can be even a little bit interactive and I can write using my pen and explain. So here is the structure. First, I want to present the problem. So I assume you all know that, but it will be useful to, you know, be on the same stage and fix notations, etc. So I state the main result and give an outline of the proof and, you know, state all the ingredients that we need. And then in the second part of the talk, I will try to give more details how to actually show these ingredients. So there will be some basics. And then, you know, I talk about fundamental invariance. I talk about highest weight vectors in plathisms and how to lift them, etc. And we'll get more and more complicated towards the end. Okay, so this is the plan. So let's start with the first part. Of course, you all know that, but let me still go through it because the problem is very simply stated and I think very beautiful and it's completely open. So it's the permanence versus determinant problem. I think it's the main problem in algebraic complexity theory. And so we see here a permanent of an m by n matrix where the variables are, the entries are variables xij. And we ask how many arithmetic operations are sufficient to evaluate this polynomial, right? This is the permanent. And we know, I mean, there is an algorithm due to Reiser, makes some inclusion-exclusion tricks, and it works with roughly with m times 2 to the m operations, and nobody knows how to do this with less operations, right? Essentially. So exponential number of arithmetic operations. On the other hand, there is the cousin of the permanent, if you want, is the determinant. So here you see this Leibniz formula here with the signs, right? So, and we all know we learn, every mathematician learns in its first year that this polynomial can be efficiently computed. Usually people think in terms of Gaussian elimination, which involves division, but you can also do without division. And I think it's fair to say that, I mean, just to understand the importance of this problem, I sometimes think we do a lot of computation nowadays in our world, and most of it is linear algebra, I think. And why does linear algebra work? And we can solve linear systems efficiently. And why can we do that? Or what is it related to? It's intimately related to the fact that you can evaluate this determinant. So the fact that this can be efficiently computed is extremely important for all applications, right? But we would like to okay, we see that it works, but why can't we evaluate efficiently the permanent? So this is the question, okay? So, right. So I should also say, of course, you can define these polynomials over any field. And of course, if the characteristic is 2, there is no difference. And for this talk, I assume I'm over the complex numbers, all right? Okay, so, and there is a valiance conjecture is also very familiar in our community. He rephrased this, He asked the following question. He said, okay, can I get the permanent? Maybe can I write it as a determinant? So what I have here is my permanent, where the entries are the variables. Now I wonder, can I write it as a determinant of a potentially bigger, maybe much bigger matrix, where the entries of this matrix are linear in the axis? And it's mathematically nicer to think of homogeneous polynomials. So that's why we homogeneous. Okay, but Valiant did not do that, but we homogenize all these things. So then these coefficients Aij actually are linear forms in the xij and some additional variable z, okay? And then what I actually compute is not the permanent, which has the wrong degree, but the permanent multiplied with this power of my auxiliary variable. And we call this the padded permanent. So, right? So this question is equivalent to the way Valiant originally formulated it. And we all know that, I mean, Puglia was the first to ask such a question, and he proved when n equals m, this is just impossible, unless n equals m equals 2. And it is not at all clear that in general such a representation is possible. So this requires some thinking, but Valiant showed it. And he showed actually if n is sufficiently big, exponential in m, then such a representation star is possible. And I think the nicest construction until now is due to Bruno Gröne. I think it's not even properly published, unfortunately. He proved, he gave a very beautiful construction showing that this is possible when n is at most 2 to the m minus 1. Very elegant. By the way, I wrote some survey which appeared in the Séminaire Lotharingien du Combinatoire, where I also put that. It's very beautiful, very short.
Yeah.
Okay.
That survey is also very beautiful.
Thank you. Yeah, it's a bit unfortunate that the Gröne did not properly publish it. Okay, so, right. And the best, okay, the best, no, this is always the sad story. I'm laughing, but that's how life is. The best lower bound still today is due to Mignon Dresser. They proved n needs to be at least 1/2 m squared. And this is, you know, a very modest lower bound, very modest. And Valiant made this bold conjecture, okay, say in 1979, he said, well, it's impossible to have such a representation yeah, for a n polynomial in M. But you all know what this means precisely, okay? We look at sequences, okay, a sequence of, yeah, I think you know what, you understand what this means, okay? Your computer scientists know what this means. Right, and of course, we are light years away from that. And it can be okay? We also know that, I mean, if you tell this to mathematicians, they may think this is, yeah, maybe some arbitrary combinatoric questions. That's how combinatorics is. There are zillions of questions, but actually, this is not just, this is a major question. One can come up with these complexity classes a la Valiant. You know that, VNP, and I think I follow Christian's notation. They call it VPB, right? And this conjecture by Valiant is actually equivalent to the separation of two very natural complexity classes. So in a way, it's some arithmetic versions of P versus NP. Yeah, and there is also there are logical connections from our usual NP conjecture to that. So namely, the following can be said. So let's assume now we have P different from NP in the non-uniform sense. So P/poly not equal to NP/poly. Then this implies the separation in Valiant's model. Actually, okay, now I'm thinking over the complex numbers. Under the generalized Riemannian hypothesis, I proved that long ago. And why this strange Riemannian hypothesis? It's only because in the Valiant model, you allow the use of arbitrary complex constants. Okay, they could give you some power. I mean, it's not like if you think of randomization is somehow like using transcendentals, and somehow the trick in this implication was to show that it doesn't help. But if you don't like this, I mean, if you think, say, over the field with two elements and so, then you can make such an implication directly, and you don't need this strange Riemannian hypothesis. So I think whatever, it is very clear that if you want to separate P and NP in the circuit model, Boolean circuit model, then we should do this first. I mean, we have this logical implication. I mean, first we have to do it in the arithmetic setting, where it's more structured, but still extremely, extremely difficult. Okay, we all know that, I think. And then, okay, so there was this important work by Ketan Malmale, Emili Zohoni in 2001, which I think for the first time made clear and, you know, made also, I mean, everybody now then became aware that this valiant problem actually should be put in the framework of algebraic geometry and representation theory. So, and one should say that this idea actually was there earlier. It was already in work by Volker Strassen, who investigated. He was after the exponent of matrix multiplication and tensor rank, and also made this connection, right, to orbit closures, etc. Okay, so what is the, so let me explain. So it is good actually also for the, it is, I think, quite important sometimes to think coordinate free. So this is not a luxury. So let me try to do it here. It helps for understanding. So I have a vector space V, complex vector, something happened here. Okay, somehow I jumped. What happened? Sorry, I have to jump back. Oh, I know I have these extra buttons. I touched one of the extra buttons and then I jumped forward. Sorry for that. Where is it? Sorry. Should have removed these extra buttons. So I'm back. Sorry about that. I'm here. Okay. So I have a complex vector space V. Then I can form the symmetric power. So actually this is the dual space. I form the nth symmetric power, right? And on this space, I have an action of the group GLV. This is multilinear algebra. Yeah. I can think of the elements of the symmetric power as homogeneous polynomial functions going from the vector space V to the complex numbers. Okay, but this is actually the algebraic structure. Okay, so then if I have an element F in this symmetric power, I can look at its orbit. Okay, here is the orbit. The orbits in general, as we know, they are not closed. So then we will be interested in take their closure. So the situation in connection with valiance conjecture is this. So very concretely, the vector space consists of the n by n complex matrices. So capital N is the dimension of my vector space V is n squared. And the determinant can be seen as an element here. Okay. I view the determinant as a homogeneous polynomial of degree n in this variable. So it's abstractly, it's in this symmetric power. Okay. And as I said, we go to the orbit closure. And by some general principles from algebraic geometry, it doesn't matter whether Euclidean or Zariski, it will give the same result. Okay. And so now this is the main, in a way, the main object of the main geometric object of interest is the orbit closure of the determinant. It's this thing. So I like to denote it by capital omega n. You know, in cosmology, there is this constant capital omega. It's like the final thing. We don't know the answer. There is the small omega is matrix multiplication. It's just small. And this is the big one. We want to know what it is, but we don't know. So this is a geometric object. It's, I think, very complicated to understand. Yeah, right. Okay. And so what do we know about it? So if n equals 1, omega 2, that's very easy. Then we are dealing with quadratic forms. I mean, it's a very easy exercise. You can even do it in your head. This omega 2 is the whole space, right? Basically, because any non-degenerate quadratic form can be put to diagonal form. I think that's all. So omega 3, so if n equals 3, that's already more complicated. And there was a paper of my student Jesko Hüttenhain with the PLRS. They determined omega 3. And right, but this proof, I'm not 100% happy with the proof, but even this proof has some component that requires computer calculations. In a way, it means there are some things that we not completely understand. And also in the thesis by Jesko, I think he also talked in this series, there is a conjecture regarding omega 4, which I believe this is true. Okay, but nobody took the effort of proving it. So we have quite a quite a concrete idea what it should be, okay? But nobody really proved it. And the difficulties are somehow related to multiplicity and singularity. It's quite tough. Okay, but so that's the, not even omega 4 we know. Okay, but I think omega 4 we could know if we really wanted. Okay, so right. So let's move on to the orbit closure conjecture. So this rephrasing of valiance hypothesis in this geometric setting. So we already encountered the padded permanent. So here's the permanent. It has degree m, right? And then we take, actually we could take any linear form, but for convenience, let's take x11 is a variable, it doesn't really matter. We multiply it with x11 to the n minus m, and then this thing is homogeneous of degree n. We call this padded permanent, okay? And okay, there is this orbit closure conjecture due to Ketan and Milind, and it says the precise statement is this: for every constant c, this padded permanent is not in the orbit closure of the determinant for dimensions m to the c, right? When m for infinitely many m. So you cannot put this here when n is m to the constant. Okay, this is okay. And this, the logical connection is that it's easy to see that this orbit closure conjecture implies valiance conjecture, right? This we know. The converse we don't know. I mean, we should be aware. I mean, probably you all know that somehow we are doing here something. Valiance conjecture was in a way, he did combinatorics. Okay, there was combinatorics and maybe linear algebra. But now in this orbit closure conjecture, we talk about this omega n, which is, what do we have? I mean, it's an orbit, and then we add all these boundary points. So it's something that potentially extremely complicated is. But why do we do that? It's actually not necessary. Valiant doesn't do it, but we are aware that all the methods that we had and we are thinking of somehow would. Okay, also, I mean, we cannot distinguish omega from its closure. So that's why we have this. So, okay, right. So we are going after this orbit closure conjecture. Okay, good. So and then there was a plan set up by our Indian friends, Ketanu Milind, how to go about this. I think some really very, very beautiful idea of simplifying the situation, like you do it in mathematics quite often when you say do algebraic topology, you know, you extract some features and hope it will still be enough information to do it. So the idea here is go for symmetries, okay? Symmetries are all important, and we have representations here. We have vector spaces with groups acting, and let's just use this information, okay? So what we have here, we have, okay, I say it now, okay, first in a little generality. Oh, okay. So I have my symmetric power, I have my group acting, right? So now, okay, so this space, this is, think of homogeneous polynomials. This is where my objects are. And then I go to the coordinate ring of this vector space. The coordinate ring is this. So this is the algebra of polynomial functions going from this space to the complex numbers. Now this coordinate ring can be written algebraically. This is just, it's a graded algebra, and it's the direct sum over the d's, over the degrees, and symmetric power of this thing. So, and actually the star goes away, but that's a detail. So we have a direct sum over all degrees d, sim d, sim n. That's what this is. Okay, and okay, right, and these elements, this sim d, sim n, they are called plathism. Okay, they have been studied in algebraic combinatorics a lot. And the question is now, I mean, these are G modules, and somehow they split into irreducible G representations. We know the group G is reductive, so it will split somehow, okay? And we want to know why, how. And it is known from the representation theory that all the irreducible G modules. They are structurally known. They are called Weil modules or Schur-Weil modules. I denote them with W lambda, and they are naturally labeled by partitions. Yes, in this case, because I'm dealing with, because of the structure, it is known by looking at degrees, and so that this must be partitions of d times n. So the number of boxes of the partition will be a multiple of n. And the partition are into at most n square parts. So I hope I did not plan to give more explanations on that part, because I assumed that it was covered in the previous.
Yes, it was. Yeah, but
covered.
I mean, if anybody has doubts, you can please ask.
Yeah. So okay. Then okay. Yeah. Christian told me
it was
last week that it more or less was
Greta,
there.
Yeah.
So, but still, I have here is a Young diagram. So what do you see? So I have 1, 2, 3, 4, 5 boxes in the first row. I put here a 5. 3 boxes in the second. I have 3, 1 box here. The total number of boxes is 9. So this notation stands for such a Young diagram with 9 boxes. And when I say length of the Young diagram, I mean the number of rows, which would be 3 here. Okay, so I have size is the number of boxes, and I have length is the number of rows or the number of parts. Okay, good. So then I already had before coordinate ring. Now I will use this notation C of omega n to denote the coordinate ring of omega n. So just polynomial functions define omega n. Right, I use this. Okay, very big object, of course. And then what I do, very general argument, here I have, right, so this omega n it's a Zariski closed subset of this space. So I can just restrict my polynomial function. So this map here that you see here is just the restriction of polynomial functions, and it's surjective and it's equivariant. I think this is best understood probably in a more abstract setting, because it's completely general. And then, right, it's surjective. And then there is Schur's lemma. It tells us what happens. When this guy, let's say here, I have an irreducible submodule here. Say it is of type lambda, is isomorphic to W lambda, a Weil module. What does it happen with this map? Well, the map is a module homomorphism. There are just two. It's a 0-1 thing. Either it is mapped to 0, it's killed, or it is mapped isomorphically. Okay, it's yes or no. This is Schur's lemma. Okay, so this is very important. So right. So then we will say that lambda, the partition, occurs in this coordinate ring, in say in the degree d part, if this thing contains a copy of W lambda, right? And yes, and I can say already by So if this lambda occurs here, it must have occurred here by Schur's lemma. That's very important. Okay, so takes time to explain all these basics, I see. Okay, there was now the Orbi closure of the padded permanent. It also had a notation. Now this we denoted with C and M. Now there are 2 parameters. M gives the size of the permanent, and the N says, okay, in which space we view it. Okay, so the padded thing has a degree N. And so here is here is the strategy. Maybe I have explained it 1,000 times. So suppose it's a simple but nice idea. So suppose the padded permanent is in omega n. We want to refute it, right? So if this is the case, then of course, the Orbi closure of this padded permanent will be contained in omega n. So I get this inclusion, right? And then again, I go to this comorphism. I have the inclusion. I go to comorphism, gives the restriction of the coordinate rings, which is surjective and equivariant, right? I use Schur's lemma. I explained it in the other situation. And Schur's lemma implies if a lambda occurs here,
it must have occurred here, right? And the plan is now to come up with a partition violating this condition. And this would be called an occurrence obstruction. But actually, if I have such an occurrence obstruction, then I have proved that Z is not contained in omega n. But it's clear one could do better. One could do better. One could even compare multiplicities. So if you look at this thing, homomorphism, the surjective one, what happens with the multiplicities? They can only get smaller. This is also a consequence of Schur's lemmas. The multiplicities, they will satisfy this. So if I would be so lucky to come up with a lambda where this multiplicity inequality is violated, then I would also have proved this. Okay, right? So we call this multiplicity obstruction. So there is a paper by Willi Dörfler, Christian Nickemeyer, and Greta Panova where in a baby situation for the very first time show that actually this can be helpful. So they have a situation where the occurrence obstruction cannot separate, but multiplicity can. Right. Of course, the hope is that very little is known in this setting, but it's a beautiful idea. Okay. So, but I won't say more about it. Okay. So here is the main result. So this Milin, Mulmer and Sohoni they had suggested the following conjecture. We call it the occurrence obstruction conjecture. Here you can read, okay. Basically, it says that you can separate the orbiclosure of padded permanents and determinants via occurrence obstructions, right? So, but here is the precise statement. And, right, it's clear if it were true, the occurrence obstruction conjecture, it would imply the orbiclosure conjecture, and it would imply, valiance hypothesis and so. But unfortunately, it's false. And this is the result that I obtained in this joint paper, unfortunately. Right. And here you can read the precise statement. It's, that it's not even asymptotic. So you have NDM, positive integers, n greater or equal n to the 25. Lambda is a partition with number of boxes, a multiple of n. Okay, the number of boxes is n times d. And if lambda occurs in the coordinate ring of the padded permanent, then it also occurs in the coordinate ring of the determinant of order n. That's, and of course, these constants exponents, they are not optimal. I mean, what could do better? Right. So this result, I mean, of course, there have been many things before. Actually, there was a whole series of works where every time it was discovered that this occurrence obstruction conjecture became more and more unlikely in a way. But I mean, maybe, so it's not surprising that it is false, but it's more surprising that we can actually prove it. And in particular, right before this paper, in the same Fox conference, there was the paper by Christian Nickemeyer and Greta Panova, where they showed a similar result that was more related to the Kronecker coefficient. So they refuted that a certain attempt to the orbiclosure conjecture via Kronecker coefficients is impossible, right? And so this was first, and then it was kind of boosted to this result. And so these two papers have some overlap, but on the other hand, there are certain aspects that are very different. Okay, so there are some. Okay, and Greta talked about it. I think she told me.
Yeah.
Okay, good. So that was the part one. Now, is there other questions so far, or? No. Okay, good. Okay, so no, I have something. I have one slide more. I have one slide more. So let's discuss a little bit more what actually was proved. So this slide is okay, it was pointed out to Avi Victorson, this observation. I think it's very interesting. Okay, you may think of right, there is the Waring rank of polynomials. So it's or symmetric tensor rank. So let's have, I have a P here. What is the Waring rank? It's the minimum number, minimum R, so that you can write P as a sum of R powers of linear forms. This is the Waring rank. And we can actually prove exponential lower bound on the Waring rank of the determinant and also of the permanent using partial derivative a la Nissan, and so it is not hard. We can do that. So one may think of proving lower bounds on the Waring rank by using these ideas, orbiclosures and or obstructions. So then what you would do, instead of the determinant, you would look at the power sum. So you would like, I mean, the polynomial that is of interest is now x1 to the n plus x to the n, etc. This power sum, and you look at this orbiclosure, we could call it PSN, power sum variety if you want, right? And actually, by the way, I believe that this PSN, it may be possible to understand it geometrically, what are the boundaries. And so I think I somehow feel that it's complicated, but it may be doable. I mean, for people in mathematics that are courageous, I think it's very beautiful. I don't know whether it will tell us about the complexity theory, but I think this somehow is not impossible, is my impression. Okay, right. But so what comes out? I'm basically with the same proof as for our result. That here we have it. You see, you can just in the statement, you replace the coordinate ring of the determinant orbiclosure by this PSN, and it still holds. So here we have this corollary. And not even that. I mean, so now I replace the determinant by the power sum. Okay, still, yes. But what's special about the permanent? Actually nothing. I mean, just thinking of the proof. You can replace the permanent by any homogeneous polynomial of degree m in m square variables. You could still prove it. So this means that our method, even though it's tricky and complicated, it's not sensitive to these polynomials. We don't use many properties of the permanent determinant. It's something very general in a way. So the outcome is that this strategy of occurrence obstruction, it cannot even be used in the weak model of power sums against padded polynomials. So you can't, almost nothing can be proven with this, unfortunately. Occurrence obstructions. Could be different for multiplicities. Okay, but we don't know that. Right. So that's right. Okay, it's a strong statement. Unfortunately, it's negative. Yeah. But, okay. Okay. So now let's move to the outline of the proof. So even though the result is negative, I think the proof is very interesting and one can learn a lot. And I think we also get new mathematical insights that are of independent value. Okay, the first ingredient is an observation due to Kadish and Landsberg. So let me, if I have a partition, I think of Young diagram. Here is the, okay, here's the Young diagram. Maybe it goes on. So I define the body. So what is the body? I just remove the first row. So this will be the body. So I call it lambda bar. Okay, so this is the body. So in Kadish and Landsberg, they proved the following. So let's assume, I look at this coordinate ring of the padded permanent. Let's assume some lambda occurs there. Then in a way I can say that, I mean, there are two things. First of all, the length of lambda, so it's the number of rows, is at most m squared. So what is behind this, the padded permanent? How many variables do I have? Actually, I have m squared variables plus the one variable for homogenization. And this is a general principle that when you do this, actually, maybe if you look at it for the first time, maybe you put here m squared plus 1 and then you look closer. So this is basically because this padded permanent only depends on m squared variables, you get this. I mean, this is the idea behind. It's not a proof, but this is a simple reason. And the second thing is very important. it says that the body of lambda has at most MD boxes. So now think of this context of valiant conjecture. So the n, it's the size of the big, the n is much bigger of m. So you should think of n much bigger than m. Okay. So then you see, so this MD, so is tiny. So in a way, okay, somehow the way I think about it, here is the body, okay. The body is very small. The body is very small compared, okay. So in a way means if I have such a candidate for an occurrence, such a lambda, just by the fact that it occurs in this permanent thing, it's essentially, it's a very long row, and there is some small stuff, you know, some small body anyway. So it's an enormous restriction. By the way, right. So by the way, I mean, there is work, okay, because you can replace the determinant by the iterative matrix multiplication and trying to go through the story. There's a paper by Christian and Greta and maybe somebody else, Fulvio, or Fulvio, I think, I'm not sure. So they show that they have some result, but it's not exactly in this context. There's a difficulty, and the difficulty is exactly here, if I'm not mistaken, because we don't have a Kaddish-Landsberg result. Okay, so we really make strong use of that. It's correct, Christian, what I'm saying? Or?
Yes, I'm not exactly sure what you are exactly referring to, but we tried to do this in different models, yes, and we have a paper with Fulvio. That is true, Fulvio. Yes.
So, but right, I wanted to say if we wouldn't have this Kaddish-Landsberg thing, I mean, everything would break down in our argument.
This is correct.
So I want to say it's very right.
It's the padding basically, and the Kaddish-Landsberg.
Yeah, the padding is, yeah, okay. Good. So the only information we exploit about the permanent in our proof is that actually we deal with the padding. Yeah. Actually, we deal with the padding of a homogeneous polynomial of degree m in m squared variable. That's all. No more information. That's all. It enters here. Okay. So this was also crucially used in the paper by Greta and Christian. Good. Then there is another property, also very important and used in the Christian and Greta paper. It's the semigroup property. So we need to prove that many partitions occur in the coordinate ring of the omega n. So how is this achieved? So it's like Lego, or I don't know, Lego. You establish the occurrence of certain basics, or maybe not Lego. There is this play where you have this little, not Lego. There's this where you have these figures and then you make some nice combinations. So you show for certain basic shapes that they occur and then you put it together. Okay. So the putting together is guaranteed by the semigroup property. And this is here. It says, okay, let's say lambda and mu, they both occur in the coordinate ring of omega n. Then lambda plus mu also must occur. Okay. And if you know a little bit of the context, the proof is very simple. So I think I will just, it's a one-liner. I will say it. You need the concept of highest weight vector that I want to define a bit later on if I have time. But the idea is this. So if lambda occurs, then it means the coordinate ring of omega n has a highest weight vector f lambda. Same, I have a highest weight vector f mu. A highest weight vector, so this is an element which is invariant under the action of the upper triangular matrices with one of the diagonal plus it should be a weight vector for the torus action, whatever this means. But now it's immediate from the definition. If you just take the product of these two polynomials, f lambda times f mu, it will be a highest weight vector. Because like product of invariance is invariance, and you check the weight is just the sum of the weights. So that's the proof. The product is not zero. That's all. Okay, so this is very simple if you see it this way. Good. Right. Good. Okay, this is the semigroup property. Good. Okay. So what are the basic building blocks? I mean, we have to start somewhere. These are rectangles. So here, okay, let me see. Do I have a picture? Oh, here is a picture. So here, okay, I have a rectangle. Okay. 3 times 4, 3 rows. But then I allow me to add boxes in the first row. So this is a rectangle to which a row has been appended. So 3 times 4, this is the format of the rectangle. And the 18 refers to the number of boxes. So we use this notation. It's very useful. Okay. So now here, okay, here is the thing. So let's say we will have the notion of an even partition. A partition is even if all of its parts are even. Okay. So for instance, this guy here is even because his 4 is even and this number is also even, which is 10. So let's assume, okay, now I have this shape. So this proposition says whenever I have such a shape, a rectangle with extended row, which is even, right? And the n, the number of boxes here, is at most k times L, then this shape will occur in the coordinate ring of the determinant in degree k, always. Okay, so you very weak condition, very weak condition. And okay, and how do we do that? Right. Or maybe, no, I want to say something different. Right. Okay, yeah, okay. The strategy of, what is the strategy of proving that? So the only property of omega n that is used in the proof, it has omega n contains padded power sums. So I will, this is the information we need. Okay, so that's also why our proof also works for the power, for the padded power sum variety. So why do we know? Why do we know that this is the case? So like this is the next thing. This is stated here. So what do we have here? Phi 1 up to phi k are linear forms. Okay, I take this power sum and then I pad it with a variable. Okay, and I say that this padded power sum is in omega n if n is greater or equal sk. So why is that the case? So this is so simple in a way that I can explain it. Okay, what is, okay, maybe I write it here. So I, instead of any forms, let me put variables, x1 to the s plus xk to the s. So it's a power sum. Then I look, what is the formula size of this? The formula size is less than s times k. No, you just do it in the trivial way. And then you use this valiant result saying that, aha, then I can get this formula as a projection of a determinant of size sk times sk. Okay, that's the thing. And then you rewrite it. Okay, what do you do? Okay, then you get this, and then you realize whether I have variables or any linear forms, it doesn't really matter. Same. And then you just homogenize to get this formula, and that's the proof. Okay, so it's actually this valiant thing here. So I think I gave one proof here. Okay, so good. So now comes the strategy. So we have the ingredients. We have Kadish-Landsberg, we have semigroup property, we have basic building blocks. Now how to combine it? Strategy of the proof of the main result. Okay.
Sorry, Peter, can you just repeat the statement of value? So we are not looking at closure at all. You're directly talking of projection there in valiance. When you're
right.
saying...
Good. Let me see. Well, yeah, okay. But you see, if I have this, then I will, and the phi 1 up to phi k, they are not necessarily independent. Correct. I mean, so I mean, here I go to closure, but in a very controlled way, in a way. You see, nothing fancy, nothing. But you are right. It's right. Okay, this is like these boundary points that I go to, they are completely harmless.
Correct.
That's very good observation. Yes, very good observation. Correct. Okay, so strategy of the proof of the main result. So let's assume I have a partition, and for simplicity, I assume it is even. Otherwise, it gets just a bit complicated, but not so much changes. Even partition. Okay. So n is greater or equal n to the 25, right? Okay. And lambda occurs in the coordinate ring of the Petit permanent. We want to show that lambda occurs in the coordinate ring of the omega n. So what to do? First observation is Kadish-Landsberg, very long row. And now we distinguish two cases. So the first case is when the degree is large. So the degree essentially tells me how many boxes. So here I have a lambda with many boxes. So the many means precisely this. So if you have many boxes, then we proceed in the Icke-Meyer-Panova paper. We take the body and decompose it into a sum of even rectangles. So what do we do here? So maybe I can, okay, this is actually very simple in a way. So I try to show you that what is behind. So this is even, okay, this is even. And then I just take this rectangle. And then I take this rectangle. Right, and maybe there is more stuff. I don't know. Maybe it's another one, but I have this very long first row. So I decompose it, and I want to write my partition as a sum of these guys that I had here. Okay, sorry, these things I want to do. These guys. Okay, but there is this condition here. Okay. So I have to make sure that this condition holds for all the components I have here. And this I can do if my degree, if I have enough boxes. So my row here is so long that I accommodate it. So then I don't give details, but that's the idea. Christian, you can correct me if I'm wrong. If the degree is sufficiently big, I decompose this even partition into a sum of these rectangles with extended first row. Okay.
Yeah, it's exactly that.
It's exactly that. Now, but then by what I said previously, by this previous result, all of this rectangle with the row, they occur. So the sum occurs, semigroup property. Okay, and I'm done with that. Okay. So this is the thing. Okay. So, but this is case one. But how about case two? Case two is difficult, is more difficult. This is really the difficult thing. If the degree is not that big, so what do we do then? Actually, this is a bit complicated. This is actually that part I have a little bit forgotten about, to be honest. Yeah, so what do we do? Right, so then we have this proposition, I called it all, I don't remember why, all, ALL. Okay, so what does it say? I have a partition lambda, right? Again, small body, and now small degree. So m times d squared less than equal n. Okay, d squared at most d divided by m. For some m, then every highest weight vector of weight lambda in sim d, sim nv, okay, viewed as a polynomial function of degree d on sim nv star does not vanish on omega n. Every, okay. In particular, yeah, if lambda would occur here in sim, so it means there is a highest weight vector of weight lambda, which is non-zero, then lambda must occur here. So, okay, so I mean, okay, I don't know whether you understand this statement is really strong. It's not a statement that just, it's a statement even about the multiplicity if you want, right? Every highest weight, take any highest weight vector of weight lambda in sim d, sim n, restricted to omega n, it will not be 0. Right? That's what it says. Okay, and what is behind this? So this is I think this is really that part where our paper has the new components compared to the Ikemeyer-Panova paper. It relies on new insights on lifting highest weight vectors in plasisms, which I believe are of independent interest. Actually, this is related to some stability problems of plasism coefficients that were, actually the stability properties were known. And I mean, we obtained new proofs in terms of highest weight vectors, and before there were proofs in terms of algebraic combinatorics and multiplicities. Okay, and then to complete the whole, I mean, the proof, we also needed to treat non-even partitions. So we needed more building blocks. So in a way, I mean, so far in my explanations, the only building blocks were rectangle and then a long row. But then we also added this thing. We added a column, you know, this with these two things, it was enough. And some tricks, it was enough to do it. Okay, so this is okay, I used up a lot of time, realize. I'm going slow. When did I start exactly? Sharp or
25? Yeah, no, actually you have what, 30 minutes left?
30 minutes.
Well, 20, yeah.
Okay, okay, it's good.
Yeah.
It's good that I did not prepare more slides. Good. So this is okay. Now I want to, so what do I want to do actually? I want to explain a little bit about this lifting of highest weight vectors. It's a tricky thing, but what I also want to explain up this proposition. Okay, where is it? My gosh. This one. Okay, I want to explain also why this is true. Okay, so what is it related to? So now come more details, but it's impossible to give all details, I mean, because it's complicated. Okay, so let's start slowly. Okay, relax. Now, I wasn't pretty sure who is my audience, so let's go to the basics. So important, and a very important idea in all of this is that one should view a polynomial as a symmetric tensor. Okay, so this was when I started with this, it was not clear to me at all. I think this only realized when we started to collaborate with Matthias Christanzl. He didn't know what is a polynomial actually. He was always thinking of tensors. So I have a vector space V. I look at these tensor power. So it's a non-commutative notion if you want. But then I focus on the symmetric tensors, on the subspace. Okay, I may think of that. Subspace of these tensor power consisting of symmetric tensors. And I have this canonical projection map, which is obtained by symmetrizing. I symmetrize over the symmetric group, a symmetrizing projection. Okay, so good. I think of that as a subspace of that. Okay, so now this is not a luxury. I think it's important actually to think coordinate free. So we have a contraction of tensors. So if I have sim dv star here, an element here, and the element sim dv, I can contract them simply because I have the contraction. I can evaluate the linear form on a vector. Okay, so this thing is not even an inner product. It's just evaluation. Okay, it's coordinate free. So I have this. Good. And then there is this notion of polarization, which says, okay, that I can view a homogeneous polynomial as a symmetric tensor. And mathematically, if I write down precisely what happens, I do the following. So I have this isomorphism from sim dv going to this thing. What is this thing? This is the space of homogeneous polynomials of degree on V star. So I start with my symmetric tensor f. Okay, how can I interpret f as a polynomial? Well, I take a v in V star, and I have to define what is f evaluated at V. And how do I do it? I raise V to the dth power. Okay, getting an element, where is it? Getting an element here, actually. And then I do the contraction. So this is the formula. Okay, sounds a bit abstract maybe, but this is very important for everything actually, for all the calculations. Okay, so in particular, okay, now let's do this. Right, so let's replace, I hope you're not confused. Let's replace V by sim NV, because what I said before was general. Then sim D, sim NV is canonically isomorphic to this coordinate ring, homogeneous part of degree D. So the point is this, I mean, I will be interested in these polynomials capital F, they will be highest weight vectors, right? And I will want to evaluate this capital F on a P here. For instance, the determinant, right? How can I do that? I will view VF as a symmetric tensor, and then I will do this evaluation. So the bracket of F with P to the dth power. That's how the calculations go, right? This is extremely important for all the calculations. Okay, it sounds like nothing, but it's important. Okay, and then there is the notion of highest weight vectors. So here are the definitions, but probably you all know that, but maybe we can go through quickly. In generality, let's suppose I have a rational GLN module over the complex number. Then the U sub n is the subgroup of upper triangular matrices with ones on the main diagonal. And the highest weight vector abstractly is a vector, is an element of this module V. It has two properties. Well, it should be non-zero. And it is invariant under the action of UN. So the upper these UN matrices, they leave it invariant. And when I act with the diagonal matrix here, F is an eigenvector. So what I get is a multiple of F, and this eigenvalue here has this shape T1 to the lambda n up to Tn to the lambda n. So the lambdas are integers. So this is a character of GLN. I hope you have seen this, I think, hopefully. Right. So and then it turns out the lambda necessarily must be monotonically decreasing. So if these are non-negative integers, I get a partition. Okay. Okay. Then right. Then notation. So this HWV lambda of the space is our notation for the vector space of highest weight vectors of weight lambda. So this is always a vector space. And the role, why these highest weight vectors? What are they good for? Well, okay. So, here is an example. It's the following important insight. When my module is irreducible, then the space of highest weight vectors, V of the weight lambda of, let's say V is a sure while module corresponding to the label lambda, then this is one-dimensional, right? So if V is irreducible of type lambda, I have exactly one highest weight vector of weight lambda up to scaling, exactly one, right? And also this lambda determines the isomorphic type of the module. Everything is described by, this lambda and the highest weight vectors. Okay, there's also a connection to invariance. We know that when lambda has this rectangular shape, before we had these rectangles, if lambda is rectangular, then one can show that actually the highest weight vector will be an SLN invariant. This requires some proof. And all SLN invariants arise this way. Okay, so the highest weight vectors are a more general concept than invariance. Okay, so this was very fast, but I assumed that you knew it anyway. I added this slide. Maybe I should have even done so. Okay, half an hour of work for nothing, but I wasn't sure. Okay, but now, how do we construct the highest weight vectors? Okay, so now this, actually. So this, what I'm writing now is known. So, okay. So what we can do here, so let's assume I have right, V, okay, now let's see, V is like C to the N, and then I have my standard basis, okay? So I form this wedge product, E1, wedge E2 up to wedge EJ. And then I realized that this is a highest weight vector. Why? Well, let's say I apply here an upper triangular matrix with one on the diagonal. So this is, for instance, I say E2, for instance, I would say E2 is mapped, sorry, like E2 is mapped to E2 plus E1, or I mean 2 times E1 or something. Then you see that by the properties of the wedge, this will not change. So it's very easy to see this is actually invariant on the reaction of this unipotent upper triangular matrices. And the weight is, what is the weight? So if I apply with the diagonal matrix, I apply to this guy. Okay, what I get out is this, the product of the first J things, and then. So I see this is a highest weight vector, and the weight, I write J times 1, but you can write it as you want. See, you can see there's a column, okay, where I have J boxes, or you can write it this way, 1, 1, 1, 1, 1, 1, whatever you want. So this is a highest weight vector, this guy. And this is my, starting from this, we can build more complicated ones. So let's say I have a partition lambda, okay. So I have a partition lambda, okay, I can, so like a partition lambda, okay. Okay, maybe it will be like that. No, maybe let's remove. So this is thing. This is lambda. Then I look at the columns. Let's say this has mu1 boxes, mu2 boxes, mu3 boxes, etc. So the mu is the dual partition. And then what I do here, so corresponding to the first column, I look at this highest weight vector. Then for the second column, etc., up to the last column, and I just tensor them. And then it's very easy to check that what I get is in fact the highest weight vector. And okay, it takes, maybe you are already tired, but it's not hard to really to prove that this is a highest weight vector of weight lambda. So this is a way to produce them, in a way, a combinatorial way to produce them. Then Hermann Weyl did it all the time, and probably it was known before. I don't know. Okay, so, and of course, these are not all. So on this tensor power, I also have the action of the symmetric group, which commutes with the action of the GLV. So I can always, if I have such a highest weight vector, I can act with a permutation, and it will also be a highest weight vector, right? And this permutation corresponds to permuting the factors somehow. Okay, but it turns out if this essentially is all. So there is this theorem here saying that the span of the permuted highest weight vector of this type, this gives me the whole vector space of highest weight vectors. And this is a consequence of Schur-Weyl duality, so which I did not recall, but I assume this was probably happened in this. Schur-Weyl duality is the most important thing.
Yes.
And it comes out of that naturally, but it's a non-trivial thing. Okay, so, right. So these are, okay, this is actually well known. But then there was the problem of how do we construct highest weight vectors in plethisms, right? So I will now, but now it will get combinatorial, and I don't want to be technical, so I will not give many details, but let's look at this example, sim2 and sim3 V. So this is to be seen as a subspace of the 6 tensor power of V, right? So I have 6 factors of, if you want, 6 positions. I number them 1, 2, 3 up to 6. Okay. So now what do? Let's consider a block decomposition. I decompose my positions into 2 blocks with 3 elements each. 1, 2, 3, 4, 5, 6, for instance. Okay. And then what I do, I want to symmetrize within the blocks. So I want to symmetrize within the blocks, all permutations here, all permutations here. But I also allow myself to exchange the blocks. Okay, I don't want to write, this is a brief product sometimes. So I do this, I symmetrize within the blocks and simultaneously permute the blocks, and the corresponding symmetrization map is the sigma 2 free, goes from the 6th tensor power to sim2 sim3, is GLV equivariant and surjective. This is a more sophisticated symmetrization that we had before, right? And then what we do, right, now we apply a general principle saying that if I have such a surjective equivariant map, highest weight vector spaces go to highest vector spaces. So here I have described the space of highest weight vectors, right? I just have the V lambda permuted. So I only have to map them under them, and I will get a system of generators. So what is written here, highest weight vector space to weight lambda of sim2, sim3 is spanned by the images of pi V lambda. Comes out. So this is, okay, that's okay. Problem is, maybe in the tensor powers, it's even possible to describe which of these things are linearly independent or not. And here it is not known. I mean, somehow it's hard to single out the basis. That's an open problem. I think a big open problem. Nobody knows. But now, what did we did? Okay, with Christian, or actually it's in Christian's thesis essentially. So this is now labeled by a partition, and not a partition, by a permutation pi. But this is a bit, there's a lot of redundancy. Okay, we can label it more efficiently. So I try to explain by example and picture. Okay, otherwise it's very combinatorial. So let's, okay, here, how do I encode these highest weight vectors? So what I do actually, maybe think first of maybe as this pi is, okay, forget about the pi. So I have this diagram. So I think of this Young diagram as encoding my permutation, say the identity, for instance. Okay, 1, 2, 3, 4, 5, 6. But then you see the 1, 2, 3, they are in the same blocks. Okay, we'll permute them. So let's put there a letter. Let's put an A. Okay, just saying that, you know, they are kind of come out in a way they will be identified, considered equivalent. Same with the 4, 5, 6. We take B, right? So good. But I can also do it, say, if I, for instance, I have this, I apply the permutation 1, 4, which means interchange these two, then I have this tableau, okay, with these numbers, and then I say 1, 2, 3, put A, 4, 5, 6, put B. So like this, the structure in the end that we use to label the highest weight vectors is this. So we have Young tableau of shape lambda, where we fill the boxes instead of with numbers, we fill them with D different letters, like A, B, C, da, da, and the order of the letters doesn't matter. Okay, so this is what we did. And okay, and then, okay, now this is, okay, so somehow we encoded highest weight vectors in plethysms by such tableau. To each tableau T, okay, to each T, we assigned a highest weight vector VT. And then what we also did, but I will not give details, they span. I mean, we gave a rule to evaluate. I mean, what is this VT? We think of it as a polynomial. And if we evaluate, okay, actually we want to think, or a tensor, we described an evaluation rule. So we can evaluate this thing, let's say, at the tensor of rank 1. Okay, here's a tensor of rank 1. And we gave a formula to what this is. And I will not give details. It's very combinatorial. So this is a sum, okay, overall assignment maps from the set of boxes of lambda to the numbers 1, 2 up to dn that are compatible with the T, meaning that two boxes that, let's say if I have two boxes that have label A, they have to go to the same block. So it has to respect this. And then this val S, these are signs. Somehow there come some permutations. You look at the columns, and then you have some permutations. I mean, it's not a permutation, you get 0. Otherwise, it's the product of the signs. So this is complicated. Whatever this is, these numbers, they are either 0, +1, or -1. Okay, enormous. And this thing is this value. And usually we are not interested in the value. We just want to know whether it's 0 or non-zero. So this is, but no more details. It's very combinatorial, but important in all of the paper. Okay. Okay. So this is somehow, but this is a very important technical component. If you think of cars, this is the engine. Actually, really, Christian is the engine master in a way. He knows these things the best, I think, not me. Okay, I'm more, you know, overview. Okay, so then I already said highest weight vector as polynomial functions. I explained again the definition of highest weight vector. Actually, I said this already. Okay, but I think okay, I said this already. I think the only important thing I want to highlight here is here. I mean, for the proof of the main result, we have to show that some lambda will occur in the coordinate ring of this omega n. How do we do it? Well, we exhibit a highest weight vector f of weight lambda and prove f evaluated at p is non-zero. That's what we do. Okay. Now this sounds easy, okay, but it's not as easy as it looks. Okay, but this is the method. Okay, this brings us to the fundamental invariance.
And here P was your power sum, no? What was P? P was
yeah. Very good, KV. Very good, very good. I mean, if we started this, you would try to take for P. Okay, maybe the determinant you don't take. It's too much too complicated. Right, the power sum is what we managed to do.
Okay.
You could also come with you could come up with the product x1 up to x2 up to xn, and then it's already difficult. I show you.
Okay.
Yes, but with the power sum we succeed. This is the key. Okay. So fundamental. Now I tell you a little bit what fundamental invariant in the end was behind this. Okay, there are many. What highest weight vectors, but these highest weight vectors actually were derived from invariance. So okay now let's assume I have all these terrible indices. Okay, I look at sim d sim n capital C to the n. This is a plethism. And now, instead of just thinking about invariants, what are SLN invariants? There is, and I assume now this small n is even. There is a result due to how he showed that if this outer degree D is less than the capital N, then I don't have an invariant. However, if the small d equals n, then I have one. Essentially, I have exactly one up to scaling. And this invariant, I like to call it the fundamental invariant, was already known to Cayley. 1850, I don't know what. It's some kind of hybrid determinant. It's amazing, huh? Okay, this is important for us. So, and I want to show you this hybrid determinant. It's close, to the determinant. But I think it's good to, let's write it as a homogeneous polynomial. Okay, so this is the thing. I will write down what it is. Okay. Okay, here it is. So let's see. Does it make any sense? So I will evaluate this hyperdeterminant at a symmetric tensor P. P is the tensor. This is the coefficient system, and I assume it's symmetric. I sum over all tuples sigma 1 to sigma n of permutations of Sn. Product of the signs. And here, so what you see, here I have my symmetric tensor. Okay, it has n legs. And what do I put here as the indices? So Okay, say I equals 1, then I have sigma 1 of 1, sigma 2 of 1, up to sigma n. So all, okay, I don't know how to say in words, these permutations, for all I, you multiply them. Now, if you think a little bit about it, let's take n equals 2. And then if you look at it, think a little bit, then you see this is actually the determinant, because then V is a symmetric matrix. Okay, now you sum over sigma 1 and sigma 2 over pairs of permutations, but if you look closely, you see the pairs is not essential. You can just sum over one permutation. Okay, it just amounts to this additional factor. So essentially, this is the determinant. Okay, so it's a generalization of the determinant. And what is beautiful about this function, it's an invariant. One can prove that f evaluated at g dot p, g in the group element, equals determinant of g to the n times f of p. So it's an invariant. And it's the only one up to scaling. Okay. So this is important. And right. So, but how do we evaluate these fundamental invariants? So I have this paper with Christian in the Journal of Algebra. What is it? Forgot. Fundamental invariants and orbit closures, where we have some systematic investigation of this, and there are many open questions. And right, so okay, what we want to prove that f of p is non-zero. Okay, and this is not so simple as it may look. So here is an example where you see the difficulty. Let's assume n is even. Okay, so I have my Cayley hyperdeterminant fnn. I evaluate it at the product of variables x1 up to xn. Okay, I'm running over time, so I'll just say what it is. What do we get? 1 over n squared, the number of even Latin squares minus the number of odd Latin squares. So a Latin square, you put the numbers 1 up to n in the square, so that in each row and each column you have a permutation. Then you look at the columns, where I have, okay, take this the product of the signs of the columns, you get a sign of the Latin square. You can say it is even or odd. Okay, and then you wonder, is the number of even Latin squares the same as the number of odd? And exactly this difference, what you get. And there is this Alon-Tarski conjecture, which says this is non-zero. Okay, is non-zero. And actually, sorry, this is the Alon-Tarski conjecture, but it is proven in some special cases. If n is a prime, for instance, it's known, but in general, it's unknown. So you see, even for this harmless looking polynomial, this is not easy. Okay, our trick was to replace this power by this product by the power sum, then we can do it. Okay, so we did this for the power sum. Okay, the trick was then it amounts to a sum of squares. So whenever you have one positive contribution, it cannot be killed anymore. So this is okay, good. So how much more time do I have, KV?
I think
I'm over time already.
Yeah.
I'm over time.
Yeah, that's sure.
Yeah, okay. Now then maybe I can try to wrap up. I can wrap up. Right. Okay, it's fine. I will wrap up. Okay. The lifting of the highest weight vectors. Let me think. Maybe one more slide will be enough. One more slide, then to say a little bit for this proposition all, which I think is the hardest thing. But just let me 10,000 feet view of what we have done. So we have constructed, so we have this placism, okay? And here this m I call inner degree, and I increase m to n, okay? So here I have a platism space, here I have a platism space. N is greater or equal m. And we have this constructed explicit lifting maps. So these are injective linear maps from here to here, somehow, yeah? And okay, I said what it is, okay? Here is the definition. Maybe I don't say how it is defined. I just say the properties. Okay, what is it? I go quickly. Okay. The definition is quite natural, but what it does, this lifting map, it maps our highest weight vectors to highest weight vectors. So even you remember I told you I have a basis of the highest weight vectors here in terms of these tableaus. Okay. Okay, and this construction is just corresponds beautifully with this construction. I mean, if you want to go from here to here, then you go to VT, highest weight vector, to VT prime. And then, I mean, what do you have to do? I mean, you have to tableau. How do you go from T to T prime? You will just add in the first row the letters. I mean, it's extremely, the combinatorial description is extremely simple, right? This is what we did. And somehow this is how we somehow managed to get, okay, right. Using that, so we could show that these multiplicities of places, now I'm simplifying a little bit, but the multiplicities of these things, they are called placism coefficients, and there is a stability property. So if I increase n, the multiplicity will stay the same, right? And so, and right, we get new proofs of that. Okay, so, right, I think I prepare too much. It's always difficult. Let's go to the end. Okay, thank you.